Yeah, so this one, let's start with the one which is here on the board. Log of, because we will use these in our in the proof of the zero free region. Yeah, so we can practice a few exercises. So yeah, so to prove this, so you can use the formula here, log of the gamma z, etc. So log of gamma z, this is equal to, this can be written as the infinite sum n equal to 1 to infinity, and then z by n minus log 1 plus z by n minus gamma, this is the Euler gamma, minus log z. Okay, so now you take the finite sum and let big N go to infinity. So if you took the finite sum, what would happen? You have here you have an infinite sum, n going from 1 to infinity. But suppose you take the finite sum, what happens? N is equal to capital 1 to n, and then take this whole thing, z by n minus log 1 plus z by n. And what does this become? Can you tell me? This becomes, what are the main terms that will come from here? This time you are letting capital N, you are taking a truncated sum. So this will give you, any help from here? What will this give me? This will give me log, one of the logs that will come will be n plus 1 factorial. No, n minus 1 factorial, because I won't go up to factorial n, plus little z, and then you have 1 plus half plus so on, but I end here 1 upon n minus 1 minus, yeah, z times 1, sorry, I get a z, and then I get a, the next term is minus z plus half log of z minus n minus half plus z log n plus z minus n, and then I get an integral which I will take into my error term. Okay, there'll be an integral here, but this will be small. Okay, so I won't bother about it. So this is just taking out the main terms from this sum. And what happens when, as n goes to infinity? Where does this go? As capital N goes to infinity, this, where does it go? This sum, yeah. So this, you recognize this as n goes to infinity. This sum, 1 plus half plus 1 plus n. Yeah, you said something. This goes where? This is 1 upon n minus 1. Yeah. And yeah, you said something. This is log of n plus little, this is the Euler, and then plus an error term, okay? Okay? This we know. Similarly, log n plus z, what does it do? So this one is taken care of. Now you have this one, log n plus z. So log n plus z, what is log n plus z? This is equal to log n plus z by n plus big O of 1 by n square. Yeah? And you know, so in this kind of cases, what you use is the Stirling's formula, which says gamma of x is asymptotic to exponential minus x to the power x minus half, square root of 2 pi. This is Stirling's formula, and you let x go to infinity. So now everything is done. We have all the terms that are required. You can verify if you have all the terms or not. Is there anything else we will need for proving proving? Yeah, there was another one I asked you to prove. That was gamma prime by gamma. And now you see, if you differentiate this one, the exercise was here on the board, but I've removed it. So if you differentiate, this was the question, I think, that gamma prime, is this the question? Gamma prime z by gamma z. This is log z plus big O of 1 by absolute value of z. This was one of the questions I said. Now, how do you get this one from what we have just got? Okay, so you have log of gamma of z, and so all you have to do is you differentiate this. Can you do this yourself? Differentiate this, then you get gamma prime z. I mean, you have a log here, so if you differentiate, you get z. You get gamma prime by gamma. And do you get the rest of the terms? Can you check? Please try to do this yourself. Okay, did you get them? Did you get the terms? Take the derivative here. What do you get? Yeah, I mean, there is a big O. Okay, so you don't have to do everything. Everything that is smaller than that will go into the error term. So what's left here? The log of z. So take the derivative, you get, what is the derivative of log of x? Is 1 by x, and then you have to take the d of x, right? So here you get gamma prime of z divided by gamma of z. Then where are the main terms going to come from? Where will the main terms come from? Where will you have, yeah? You can, yes. You can use this. Yeah. So that's it. That's all that you have to do. Differentiate and you get log of z. And then there was one term here, this integral, but this is small. Okay. It is small, so I don't care. I take it into my big O term. Okay. Plus a big O term. Yeah. Because this is small, this integral. So okay, good. With these tools now, we will try to complete the proof of the, what was that? Zero free region. So the part that we did not do was when chi was complex. Remember, chi was complex. So chi here is, so these are tools, okay? These are tools. It's nice to see how they work. I mean, they're interesting in themselves, but for us, this was not the main thing we wanted to do. The main thing we wanted to do was to get a zero free region, which we started this morning, and which actually imitates very much the result for the Riemann zeta function. Oh, among the books, this morning we were talking about the books. Among the books that you can read, there is Apostle, which is very easy. Okay, Tom Apostle. This is very easy. You know, you can do everything. You can just read it at 10 o'clock at night and sleep, and it's okay. It's easy. That's the easiest book, according to anyone. According to me, the hardest book is Tishmash. Okay, because he's an analyst, and then he does everything the way an analyst would do, and which we would not necessarily do. But it's very complete. You can also do that, the Riemann zeta function. This book is called Tishmash. And then there are more modern books, like, as I said, Montgomery and Vaughan. We have a list did you get a list? You got a list. So Montgomery and Vaughan is maybe a bit overdone. They talk a bit too much, but it's okay. They do everything. Everything. Okay, you can, at a point of time, you'll get bored of Montgomery and Vaughan because you'll find that he talks too much. But it's good for learning, I think. Yeah. So which other book? Davenport is also good. Yeah, Davenport is good. I don't know, what have you all read till now? Any books? Have you read any texts of analytic? Have you read Davenport? Okay. Huh? Apostle and Davenport you have read. Okay. This was a course in analysis or in number theory? Number theory. There's also good old Hardy and Wright. If you feel like, you can read Hardy and Wright as well. But then don't try to read everything at the same time. Like, now I want to do the part that so these are results which we will use to okay. So where was I? So this is the exercise was, let this one now, chi square now is not equal to chi 0. Yeah, because chi square being equal to chi 0, we have done that. This is the part, as I said, that imitates very well the zero free region for the Riemann zeta function. So you're actually getting 2 for the price of 1. You have this, and then you don't have to study for the Riemann zeta function because you've already done it here. Yeah. So chi is, of course, you remember, chi is a character modulo Q. And our aim is to show that we can find an absolute constant, absolute positive constant C greater than 0, absolute, such that what? What is the statement? Such that the L function has no zeros in a certain region. So which region is this? Sigma is greater than 1 minus C log Q absolute value of T plus 2. Yeah. And this time there is no third clause. There is no such thing that except in the case when chi is quadratic, and then there may be at most 1 0 in this region. There won't be any. There'll be no zeros in this region. This is like the Riemann zeta. Yeah. So what do? We do a bit like how we did before. So proof. I think I quoted this result this morning. I don't really remember, but did I talk about this? Minus 3 L prime sigma chi 0 by L sigma chi 0, okay, minus 4 real part of L prime sigma plus IT chi L sigma plus IT chi. This is an identity, okay, and someone told me this morning that from where such an identity is expected to come, real part of L prime. So here I don't need here I have already, there's no IT, I just have sigma here. And you have sigma plus IT, and again I have sigma plus IT, and this is chi square L sigma plus IT chi square is greater than or equal to 0. And now tell me why you expect such a thing. I think you said that. You said something, Rina, this morning. What did you say? Plus cos 2 theta. Yeah. So this is positive. Yeah. Huh? Sigma plus 2IT. Is there a 2? Oh, if it doesn't very much matter whether you put a 2 or not, because yeah, but the fact that you have, it's okay. This is more correct. What you're saying is more correct. Okay, so this is greater than 0. Yeah, and here I have t is real and sigma is greater than 1. All right, because we know that 3 plus 4 cos theta three plus 4 cos theta plus cos 2 theta, right? This is greater than or equal to okay, good. And now what do we want to do? Notice that it's important. This point is important. I mean, psychologically it is important. Yeah, you guess it is important because otherwise, why would we separate the two cases? That's the psychological reason. You can't write that in the exam. You have to write that something more mathematical. Mathematically, if you don't have this if chi square becomes equal to chi 0, then over there there'll be a chi 0. Yeah, so that's not that's not going to give you the inequality that you want. Yeah, that's why we needed to do the other part separately. Yeah. Because if that were not the case, you would have no Ziegel zeros also, psychological reason. Yeah, so okay, this is very equal to 0. Yeah, all right. So now what we do is now notice I'm going to take these terms now, L prime and sigma chi 0 divided by L sigma chi 0. What is this? We talked about it several times, sigma chi 0. Let's take the negative here. And this is equal to, we did this already several times, so you must be knowing this by now. What is it? Help me. Sum. So I will get an infinite sum of what? I get a chi 0 n, then I get a von Mongold n, and then I get n power sigma, and I let my n go from 1 to infinity. Is that right? And this is therefore less than or equal to, what is this less than or equal to? I can forget this chi, and then I'm left with lambda n by n power sigma, and that, what is that? Yes, that is zeta prime of sigma, and zeta of sigma. I had a negative somewhere, so there should be a negative somewhere. And this again, now let's go back to our construction of zeta prime by zeta. And what was that? What was that? We are not, huh? Where? Where? There is a negative. Here. Here. Where do you want the negative? No, there is a negative on this side. Yes. Yes. Though there should be a negative here. Yeah. So, and this one, you know that, you know the way we write the zeta function, which we've done several times. I mean, even before I started, you already saw that. This is less than, what is it less than? 1 upon? Yeah, but the main term, the first term is? Yeah. And then there is some constant, yeah? I'll call it C1. C1 is a constant, yeah? Is that okay? So I will be able to bound, I will be able to write L prime by L. I have a bound for L prime by L, all right? And this constant is positive. Okay, Wonderful. Now, do you remember that for zeta of S, we had a completion of zeta? You remember for zeta of S, we had a completion of zeta, and I think you used C for that. So we'll use that again, but this time with the chi. Yeah. So with the chi, this is just like, so with the chi, what was it? It was so I have never been very good at writing the C. I don't really like it, but because I don't write it well. So this one, this for S chi, yeah, this is the completion. And how does one write it? Do you remember the one for without the chi? Without the chi, it's how is it written? It's written like this. S, yeah, without the, when chi is 1, this is equal to, anybody can help? Yeah, S into S minus 1 by 2 gamma of gamma of S by 2, yeah, pi minus S by 2 and zeta S. All right, but that's not the one I want. I want the one with chi. So this time I'm going to get Q. I'm going to get a Q, and I'm absolutely obliged because chi is a function modulo, chi is a L function modulo Q, with a, not modulo Q, that's not correct. It's an L function whose modulus is Q. So S plus A by 2 gamma S plus A by 2 L S chi, yeah, and this A depends on whether chi minus 1 is 1 or minus 1, okay. A is either equal to 1 or minus 1 depending on, A is either equal to 0 or 1, A is either equal to 0 or 1 depending on whether chi minus 1 is equal to 1 or minus 1. Okay, so notice that when Q, this can degenerate to the case of the Riemann zeta. All right, and it is known that this can be written as this whole thing. Okay, this is the definition, nothing else. Okay, we know that. What do we know? If I write this completion, then S chi, this is equal to exponential sum A plus B times S into product of P 1 minus product of rho 1 minus S by rho. Okay, I forgot, exponential S by rho multiplied by exponential S by rho. So now if you take this as a black box, okay, a blue one if you like. And now if you want to do the same thing as exists here, what will you be doing? You'll be taking the derivative, and you're going to get C prime by C. Okay, so what will you get? You will get T of so S chi of C of S chi And the real part of this, what will the real part of this be equal to? Have a look at this way of writing it. This will be equal to, from the exponential, what will you get? B. So it will be equal to the real part of B. Good. Then from the product, what will you get? So you'll get a sum of rho. Okay, rho is the other zeros, yeah, and you will get, so this will become 1 upon s minus rho plus 1 upon rho. Is that okay? This should not be here, it should be written here. Okay. Does this ring a bell? The sum of rho 1 upon s minus rho plus 1 by rho, does it tell you something? Does it tell anybody anything? It should. It's gamma prime. Yeah? So now if I go back and take this, so if little a is 0 or 1, yeah, for little a being 0 or 1, real part of this real part of C prime S chi, okay, by S chi. If I take the real part of this is equal to half log q by pi plus real part of, that's what we did before, gamma prime s plus a by 2 and 2 gamma s plus a by 2. All right. Plus, I have that last thing over there, real part of L prime S chi L S chi. All right. So now separate this and bring it out on one side. So this gives, which one am I going to bring? The last term over there, minus real part of L prime S chi by L S chi. I write it on one side, and then I have all these terms, yeah, is equal to this one plus this one plus this, yeah. So this is equal to half log q by pi plus real part of gamma prime s plus a by 2 gamma s plus a by 2, but with a 2 outside, minus real part of b. This is the b that is going to come from here. Okay, this real part of b, and minus what I had here, this one, rho sum over rho real part of 1 upon s minus rho plus 1 by rho. Why? So you know, okay, one thing that I should tell you is that when you write the completion here, okay, we know something. We know that we know something about this a and b. So e to the power a, this is equal to c 0 chi. You may need it, even if you don't need it just now. And the real part of b this is equal to sum of real part of 1 by gamma minus. Yeah. So now I'm going to put that real part instead of real part of B, I'll put the sum. So now what happens? I don't have to calculate everything. I just have to get a constant. Yeah. Don't calculate like as if you have been employed just to calculate. Do it only when you have to do it. Yeah. So now, this one we just worked that out in the few 2 or 3 things that we did in the beginning, and so this becomes okay. So this is less than C2 log some constant log Q T plus 2 minus the sum of real parts of 1 upon S minus rho, because there'll be a 1 by rho here and a 1 by rho here, which will cancel out. Okay? By what we did before. Now, what do you know? You know that the if, so what do I have? I have the 2 possibilities. Either the chi is primitive or it is not. Okay. If it is primitive, then what happens? Then the sum of the real part of 1 upon S minus rho is always positive. Yeah. So if the who is it? If the character is primitive, what happens? We get this one, real part of 1 upon S minus rho. This is positive, yeah? That means that minus, so I get minus real part of L prime by L if the character chi square is primitive, then minus L prime by L, this will be less than. So 2 possibilities exist. Let's do the first. Chi square is primitive. So I get the term on the left minus real part of L prime S chi square. This is less than some constant C2 log Q absolute value of T plus 2. Okay? The other possibility is if chi square is not primitive. If it is not primitive, then by definition, there exists some chi1, it is induced by some primitive character, which is, let us call it chi1. Okay? And in that case, we go back to the equation we had. So case 1 is done, okay? Case 2, minus real part of L prime sigma I plus I tau chi L sigma plus I tau chi. This is less than C2 log Q T plus 2, okay, minus 1 upon sigma minus beta. So what happens, 4 times sigma minus beta is less than 3 times sigma minus 1 plus C3 log of Q T plus 2. So choose your, this is just, if I take it 4, it's small enough, fine. I mean, it didn't have to be 4, it could have been something else. But the point is, I want a good sigma, so I take my sigma. What do you want your sigma to be? It's done, the sigma is done. I choose sigma now. What do you want to choose sigma to be? Sigma has to be greater than 1, remember? So choose it to be here 1 plus. And then what would be a natural choice? Natural choice would be this log Q business, right? So delta, some delta log Q P plus 2. Yeah. And with delta should be just small but positive. With delta sufficiently small, and that's up to you to make it small. So you can do that to get, what do I get? Beta, my dear beta has come back, is 1 minus some constant, let's call it C4, and log Q absolute value. Oh, I think my tau changed to T somewhere in the middle of the proof. Not in the middle of the same proof, but I think right from the beginning I had a T instead of a tau. I hope that doesn't create any confusion. And then I have found my beta. Are you clear about why we had to separate the cases? Is that clear for you? Why the case separation was necessary? Is that clear? Because why did we do this now and the other part before? Or why did we get different results? Is the philosophy clear? Not the. What is the point in separating the complex from the quadratic? I mean, do one of the proofs go over for the other one? Could we have written a common proof for the two of them? My question is it clear to you why in one case we get a possible zero and in the other case there is no zero? I mean, clearly this is the easier proof. Is it? This is the easier proof. This is the easier case. That's why it was an exercise. I told you there's always a psychological part. That's the easier. This is the This is the part that imitates the Riemann zeta function. Yeah. So what happened here? What happened here, which would not happen for the complex? I mean, now here things are complex. And what would not happen for the quadratic case? What was good here? Yeah, the chi0 square which you got, remember? If it became, if you had chi is equal to chi0 square, then you would not be able to do this. Yeah. So that was what was nice about the chi0 square. Square existing. Like sometimes we think that it becomes more complicated, the existence, but it is not, because chi0 square was used here. Its existence was used to get this, and this did not happen in the first part of the proof. You can try to write out the proof on your own, the whole proof on your own, and see if you actually understand this. Yeah, I mean, you can use a book. There's no harm in using a book, but see that you understand everything. Okay, uh, on the non-vanishing of the Riemann of the LS chi function, and how the Ziegel zero appears here. Yeah. Yeah. Oh. Okay. Let me see. Ah. Yeah. What was the statement of the theorem? The theorem said that there exists a constant C such that there is yeah. No, this is correct. There's nothing wrong in this. I mean, I don't think there's anything wrong in this. You know why? Because you want to show that there is no zero. I want to prove there is no zero. Yeah. That would mean that there is a zero. But I don't want a zero. It's a zero-free region. So, no, it means that means that if there were a zero, beta would have been greater than this. So there is no zero. And here also there is no zero, not only for the complex case, in both. There may be an exceptional zero, at most one. You're right. Yeah. So any zeros that should be less than or minus equal. Yes, yes. So is there something wrong in somewhere? I mean, that is correct, but if we choose arbitrary small delta, that
The last line should be less than x.
Oh,
If I
okay.
calculate
Okay. Yes, yes. I see your point. Yes. I see what you mean. Yeah. That is why I want to take delta to be small. That's why I want delta to be small. Because if I take delta to be small, then beta is smaller than this. And then I have found my constant such that the, yeah, so that's 0 free. So is the proof now, is the proof complete, and are you convinced that about the 0 free region of the, now you can do one thing, you can try to write it for zeta. It will be very easy to write it for zeta, because now that you have seen it in general for the L function, writing it for the zeta function will be easy. Yeah. Anyway, yeah, you see that there will be no case. You can do this as an exercise. You can try to write it on your own and then see. It's there in all major texts. You'll find the proof for zeta. So try to take the proof and do it without the q. I mean, q is 1, and see what happens. Yeah. Well, this is not really the classical way of doing it. Usually people do the zeta first and the L afterwards. But we've done the L first, and then we try to see if the...
sigma, right? Sigma, not delta equal to.
No, certainly not delta. Yeah, you're right. Yeah, so that's, you're perfectly right. It's sigma. You can choose delta equal to 1 plus delta.
Because of this, you are getting the real part of this to be
Yeah,
positive, right?
It's sigma. Yeah, that's why. Yeah, okay. Okay, so I suggest you do this work, and you try to write out, first you see if you understand the proof completely, and now the next things that I will do will be the prime number theorem in arithmetic progression. I expect to do it, but somehow I think that I will not be able to finish the proof in 2 hours. I'll try. And then, so today is Tuesday, so we have 3 days. And then one day we do the ternary Goldbach, and one day we do the binary Goldbach. I mean, ternary Goldbach can be done, and binary Goldbach cannot be done. No, ternary Goldbach. Huh?
You mean by help of the.
Yeah, I will show you how the sieve method is used for that. And for the binary, the interest is to show its relationship with the Siegel zero. Okay, what is its relationship with the Siegel zero? That's the interest. Okay. Okay. So thank you for listening, or to all the difficult things that I said the whole day.